Let's now look at some properties of a Laplace transform. So we talked previously about the Laplace transform and its definition, and we even saw a table, and that table had several specific Laplace transforms, but that table actually had more Laplace transforms than are really needed. And so, for example, let's suppose I have a function f, and the Laplace transform of f is some function big F of s. Then the Laplace transform of e to the at times f of t. So take any function we have and multiply it by an exponential. That's just the Laplace transform of the function, but we replace s with s minus a. And so let's think about this. In the table, I know the Laplace transform of 1 is 1 over s. And so what happens now if I multiply that by e? And let's do e to the 4t. Well, according to the theorem above, I would just replace s with s minus 4, and that's actually the Laplace transform in the table for the Laplace of e to the 4t. And so you can kind of see how that's related. Similarly, and these theorems don't necessarily go in the same order as the textbook, let's let f of t, oops, nope, sorry, looking at the wrong theorem. Let's try that again. So if the Laplace of f equals f of s and little f of t is piecewise continuous, oops, I did piecewise twice, is piecewise continuous on our interval 0 to infinity, which is where our Laplace transform is defined, then what about the Laplace transform of t to a power times f? What is that? Well, it is going to involve the Laplace transform of my function, but probably not in the way you think. So it's going to be negative 1 to the n, an alternating piece depending on what power I have. And then it's going to be the nth derivative of my Laplace transform with respect to s. Now this is the derivative of the Laplace transform. So remember, it's derivative of s, or derivative with respect to s. It is not the derivative of the original function. So for example, what if I wanted the Laplace transform of t squared e to the 4t? Well, I know the Laplace of e to the 4t is 1 over s minus 4. This is t squared, so I'm going to take negative 1 squared times the second derivative of 1 over s minus 4 with respect to s. So the negative 1 doesn't matter, it's going to go away. Well, what's the derivative of 1 over s minus 4? Well, I could rewrite it as, oops, not that though. I could rewrite it as s minus 4 to the negative 1. So I would have negative 1 over s minus 4 squared, but I need to take the derivative again. And so the derivative again would be 2 over s minus 4 cubed. And if you look at the book, that's 2 factorial over s minus 4 to the 2 plus 1, which is what the book says I should get for t to the n e to the at. So these two theorems tell me that I could have actually given you fewer pieces in that first table. Okay. All right. Now let's go to two theorems that will kind of get us to where we want. We're wanting to do differential equations. So far, I haven't said anything about what happens when I want the Laplace of a derivative. So now let's talk about what happens if I want the Laplace of a derivative. And this is where I started to write. So let f of t be continuous on our interval 0 to infinity. Oops, don't really want that period there. And f prime of t piecewise continuous. Now that's the second time I've used piecewise continuous. We talked about piecewise functions earlier. So those don't have to be continuous, but they have to be continuous in pieces. So I can have jumps, but I have to have a finite number of breaks. So then, if I have f is continuous and f prime is piecewise continuous, I can find the Laplace of the derivative. And the Laplace of the derivative of f is simply s, Laplace of f, so s times the Laplace of f, minus my function at 0, or f of 0. So notice I would have to have an initial condition here. Now, one note here, and I'm going to do this in red. The book is using this notation. So they're doing that extra parentheses s after the Laplace transforms. Notice that does not mean times s here. That is still function notation. And so that can be a little tricky. All right. This really isn't a theorem, so I'm just going to star it. It's kind of an extension of the next theorem that I'll do. But let's let f of t and f prime of t be continuous on 0 to infinity, and f double prime of t piecewise continuous on 0 to infinity. So now let's extend this. So what's the Laplace transform of the second derivative? Well, if I follow the rules before, it would be s times the Laplace of f prime minus f prime at 0. But I'd like to adjust that. I know what the Laplace of f prime is, so that's s times s Laplace of f minus f of 0. That was the previous theorem, and then I still have the minus f prime. Or multiplying that out, the Laplace of f double prime will be s squared Laplace of f minus s f of 0 minus f prime of 0. And then putting that together in our final theorem, if we have, so let f of t, f prime of t, all the way down to the n minus first derivative be continuous on 0 to infinity, and the nth derivative piecewise continuous on 0 to infinity. Well, then I can take the Laplace transform of the nth derivative of f, and that will be s to the n, Laplace of f, minus s to the n minus 1 times f of 0, minus s to the n minus 2 times f prime of 0, and that pattern will keep continuing, minus a whole bunch of dots, minus s times f to the n minus 2 derivative, and then minus f n minus 1. And so you can see that I could use this now to do Laplaces of derivatives, which will be handy when I have to do Laplace of differential equations. Okay. So these are a couple of properties along with linearity. I can pull constants out, I can split up sums and differences, I can now multiply by exponents, I can multiply by t to powers, and I can also do Laplace of derivatives. And so you'll be asked to apply these to find some Laplace transforms. But there are some properties of Laplace transforms.